This presentation looks at the problem of detecting small moving targets in digitized sensor images. In particular, it is concerned with detecting these targets under extremely unstable conditions, such as when the sensor or the vehicle carrying the sensor is moving. This problem is somewhat analogous to watching a movie filmed from within a moving car on a very bumpy road. If the camera is shaking around too much, it can become very difficult to see what is going on. A sensor is like a camera. If it moves too much, its images, like the pictures in the camera, become distorted and smeared. If the purpose of the sensor is to watch for moving targets, then this instability, known as jitter or drift, could allow these targets to pass through undetected. This thesis will show that by measuring the jitter in the images and then using a combination of bilinear interpolation and resampling to remove the jitter, thus stabilizing the background, that the probability of target detection will be greatly improved in very unstable sequences, and that many targets that were previously undetectable will now leave very strong tracks. Displayed here is a simulated satellite infrared image taken of an area in the Nevada desert near Lake Mead. Because of the distance, little detail except for the shoreline is actually visible. If we zoom into a part of the shoreline in the image, we can see that the image is actually composed of many solid squares of various shades of gray or intensities. Each square represents what is known as a sample or pixel of the image. The intensity of a pixel represents the average intensity of the actual background it covers. If most of the pixel covers cold water, then the pixel will be dark. If instead it covers hot desert sand, then the pixel will be light. Lastly, if both cold water and hot sand are covered by the same pixel, then their intensities will be averaged to a warm shade of gray. Each pixel in the image is associated with a numeric value representing that pixel's intensity. These numbers can typically range from about minus 32,000 to plus 32,000. The numbers in our image of Lake Mead range from about 9,000 to 21,000. When an image is displayed, these numbers get converted into shades of gray. Basically, the lowest number in the image, 9,000 in our case, gets displayed as black, while the highest number gets displayed as white. The numbers in between, then, get linearly scaled to shades of gray between black and white. The number of possible shades of gray depends on the method of display. The images in this demonstration have been scaled to 256 different levels. If the image gets modified such that the lowest and/or highest values change, then it gets rescaled before it is displayed. The new lowest number now is black. The new highest number is white, and everything in between is linearly adjusted. For this particular image, each pixel covers an area of 24 meters by 24 meters. Collectively, these pixels make up an image array. In this case, the dimensions of the image array are 64 rows by 64 columns. The total image shows an area which is approximately 3/4 of a square mile. 24 meters, the size of one side of a pixel, is known as the resolution of the image. In other words, the smallest detail that can be seen or resolved in this image must be at least 24 meters across. Anything smaller would just blend in with the pixel. Note that a small aircraft, such as an F-4, is normally not this large. Let's zoom in on just one pixel and see what the image resolution means to us when an F-4 flies through. On the left, we now see a single pixel greatly enlarged. Clearly, it's just a solid shade of gray. On the right, we see a scale drawing of an F-4 aircraft. The F-4 is 19.2 meters long, which is slightly shorter than the 24-meter length across the pixel. If we superimpose this drawing of an F4 over the pixel, we see that it fits completely inside. As a result, all of its detail will blend into the background, and again, all we are left with is the solid shade of gray. If the target is smaller than a pixel, how then can we detect it? We can detect it because it moves, and as it moves, it shows us its path. Of course, as was shown earlier, if these were real images, we would never see the F4 as it is shown here. It would appear instead like the sequence on the right. Even though you can't actually see the F4 in this sequence, you can clearly see that something is moving. This is because, as it flies into a pixel, it affects that pixel's intensity, making it either lighter or darker, depending on the relative intensity of the target. Then, as the F4 continues to move from one pixel to the next, you can detect a pattern of intensity changes along the target's flight path. Each time the target moves, we are actually changing to another image with the same background. We refer to these images as frames, since they are like frames in a movie. This method of viewing the data is a common target detection procedure known as a loop movie, since the same movie sequence is looped through several times. We are currently watching a 4-frame loop movie. If we stop the movie and look at just one frame, there is no way that we can tell that there is a target there. It is the movement that gives it away. Notice that in each frame, the target just happens to be located totally within the boundaries of the pixel. This means that all of the target's signal, or energy, is averaged into the same pixel. This, of course, is not always the case. Often the target will be overlapping into other pixels. How will this affect the target's detectability? If the target is overlapping into other pixels, then only part of its energy gets averaged into each pixel it overlaps. In other words, the target's energy gets split up. As a result, the intensity change is not as apparent, and the target is, therefore, more difficult to detect. The type of sensor that produces images like these is known as a mosaic sensor. It is called this because the sensor actually consists of many detectors held together in a focal plane array. Each pixel in an image is the product of one of these detectors. The key element of a mosaic sensor is that each of the detectors, in a sense, takes a picture simultaneously. In other words, the 16 pixels in our blinking image here are all produced at the same time, as if they were 16 individual pictures. Each of these pictures are then put together, like a mosaic, to make up the image. Mosaic sensors are usually designed to operate in different modes. Examples are stare mode, where the sensor is forced to lock its stare onto some point on the ground for a period of time. Auto track mode, where the sensor locks onto a target and then tracks it. And push broom mode, where the sensor is not locked onto anything so that its field of view changes as the vehicle carrying the sensor moves. Currently, there are no known mosaic sensors aboard orbiting satellites. Satellite images, with which we are familiar from weather forecasts and so forth, are created by a different type of sensor known as a scanning rather than mosaic sensor. A scanning sensor normally consists of only one detector, or a row of detectors, which over a period of time scans a region to create an image. It is normally not as effective at detecting targets, since it does not stare at a large area for any period of time. A few experimental mosaic sensors are currently in existence, which are being tested aboard aircraft. As of now, scientists are relying on the images from these aircraft-based sensors and/or simulated satellite images in order to develop and test algorithms and to design and plan experiments for future space-based mosaic sensors. All of the mosaic images used in this presentation were simulated. Let's take a look at what was involved in creating these simulations. All of the images and targets that you have seen and are about to see were simulated from this actual low-altitude, dataless image of the Lake Mead area. An accurate sensor simulation program known as SuperSim was used to produce the simulations. During this presentation, pay close attention to the shorelines and to the two very small canyons that can be seen running vertically in the image. Using Fourier transform techniques, the image was compressed and degraded in order to accurately simulate high altitude and optical blur, and to maintain the spatial high frequencies of the original image. This is the image before simulation. And this is what we get after. Essentially, an image that was taken from an altitude of a mere 2 miles was transformed to appear as if it were taken from a satellite orbiting in space. Notice that with the decreased resolution, much of the detail in this simulated image has been lost. This is because each pixel now averages a larger area, which means that fewer pixels cover the entire scene. As a result, features such as the shoreline and canyons, which previously appeared to be smooth, are now very ragged. In the simulation process, several frames are actually created where each frame is shifted slightly from the next. This allows us to simulate random jitter and drift. Real jitter is usually caused by small vibrations of the sensor, either as the result of mechanical movements within the sensor or because of movement of the vehicle on which the sensor is being carried. Shown here is a loop movie sequence of 16 frames exhibiting jitter. The same sequence is being shown over and over, as will be done with all movies in this presentation. This jitter is considered small and is fairly typical of how real data often appears. Sometimes, though, the jitter can get quite large. Jitter this large can commonly be found in stare mode data, where the sensor had trouble locking onto a fixed point. Other causes could be turbulent air on an aircraft or repositioning on a satellite. Of course, faulty mechanics can be the cause under any conditions. Real drift is caused either because the sensor is physically moved or repositioned, and or because the position of the satellite or aircraft changes from frame to frame. Here we see a typical case of small drift. But again, as with jitter, drift can also become quite large. This sequence actually consists of big drift with a little jitter added. The data gathered while the sensor is in auto track mode will exhibit some of the same characteristics and problems as those found in large jitter sequences. This is because as the sensor is tracking the target appears to be relatively motionless within the field of view, while the background is moving behind it. Both jitter and drift are measured in terms of their size in relation to the size of a pixel. If the sensor is shaken, and as a result its field of view temporarily shifts 12 meters in a particular direction, we say that the frame jittered 1/2 pixel, bearing in mind that the size of the pixel is 24 meters in our example. The sequence we see here is drifting about 3/4 of a pixel per frame. The jitter is less than 1/10 of a pixel. Jitter and drift are also functions of the time between frames. An airplane, which we think of as exhibiting a lot of vibrations, can produce fairly stable frames if the frames are taken very rapidly, such as 100 frames per second. On the other hand, a satellite, which we think of as being very stable, might produce frames with significant drift if the time between frames is long, say 10 seconds. As we will see later, large shifts, usually exceeding 1/2 a pixel, can be very destructive to the signal coming from a target. The next step in the simulation was to add a small moving target representing an F4. The size, shape, intensity, and velocity of the target, the size and intensity of each pixel, and the jitter and drift of the frames were all taken into account for the target simulation. Looking carefully, the target can be seen moving from left to right across the middle of the image. A smear factor was even modeled in the simulation. Smear is analogous to the effect created when a photographer uses a slow shutter speed to take a picture of something moving very quickly. The object that is moving gets blurred or smeared in the photograph. Lastly, random Gaussian noise was added to model flaws in the sensor. If you look closely, you can see that the pixels in these images seem to be twinkling. In real images, this is caused by electronic instability in the sensor. The specifics of the simulations are shown on this chart. All of the target detection procedures described herein were also performed and tested on actual mosaic sensor data with real targets. This data, though, is not available for publication. The results of these tests were consistent with those obtained from the simulated data presented in this report. Let's take a closer look at the target detection process and demonstrate the problems that occur when background, jitter, and drift become extreme, the focal point of this thesis. Displayed here is a short loop movie showing a sequence of 16 perfectly stable frames with no jitter or drift. The target can be seen moving from right to left in the lower part of the frame. The two dark areas at the top and left are small parts of the Lake Mead shoreline that just barely fell within the field of view. Next, we see the same sequence, but with a small amount of jitter added. The maximum jitter in the frames is approximately 0.5 pixels. In other words, the frames never shift more than half a pixel at any one time. It is still possible to see the target. Finally, we again see the same sequence, but this time with a large amount of jitter, up to 3.5 pixels per frame. Notice now that it's difficult to tell whether the target is still there or not. It's there, but the changes in the background make it almost impossible to see. As we will now see, conventional target detection methods will completely miss this target because of the large jitter. The basis of any target detection method is an algorithm designed to enhance the data in order to increase the target's signal-to-noise ratio. Many algorithms for this purpose have been proposed and tested. Previously, though, none that are known have been able to detect weak targets in high jitter data, such as our last sequence here. The purpose of this report is to present a new algorithm called background stabilization, which can detect these targets. Before we actually introduce background stabilization, though, let's first look at another enhancement algorithm known as frame-to-frame differencing and see how well it can perform on these three sequences. Frame-to-frame differencing is probably the simplest and most commonly used method for enhancing targets. When appraising the effectiveness of other enhancement methods, frame-to-frame differencing is usually the standard of comparison, as it will be here. Frame-to-frame differencing means the pixel-by-pixel subtraction of one frame from another, resulting in a new frame which shows these differences. The basic principle of differencing is that if two frames are identical, then subtracting them will result in a new frame of all zeros. On the other hand, if a couple of pixels change from one frame to another, such as a target that has moved during the time between frames, then these pixels won't subtract to zero, but to some other value, which will now be easy to detect amongst all the zeros. Unfortunately, if a lot of pixels change, such as what happens if one frame is shifted from the other, then the resultant difference frame will be comprised of many different values, rather than mostly zeros, and may be useless for finding the target. In the diagram shown here, each grid represents an image frame, such as the Lake Mead scene, while each square within the grid is a pixel of that frame. In this case, the frames are only 5 rows by 5 columns in size. The numbers shown inside some of the pixels in the top set of frames indicate the intensity or gray level of that pixel. A high number would indicate that that pixel is light or high intensity, while a low number represents a dark or low intensity pixel. The bottom row of frames shows how these numbers translate into shades of gray. When we difference these frames, each pixel in one frame is subtracted from the corresponding pixel in the other frame to produce the corresponding pixel in the new frame. For example, if a particular pixel has a value of 95 in the frame on the left, and the same pixel has a value of 15 in the next frame, then the difference will be 95 minus 15, which equals 80 in the difference frame. Recall from our earlier discussion on image scaling that when an image is modified, it gets rescaled for display. This is true with our difference frames. Numbers in a difference frame tend to range from negative values to positive values, which are approximately equal in magnitude. Ideally, the mean average of the difference is 0. This means that the difference frame is now scaled between different values than were our original frames. This can cause some confusion when looking at the frames. For instance, a black pixel in the second frame subtracted from a black pixel in the first frame might result in a light gray rather than black pixel in our difference frame when scaled with the relative differences of the other pixels. When we want to difference several frames, such as the sequence of 16 frames of Lake Mead shown earlier, each frame is differenced with frame 1. So frame 1 minus frame 2 produces differenced frame 1. Frame 1 minus frame 3 produces differenced frame 2, and so on. We end up with one less than the number of frames we started with. Since we had 16 original Lake Mead frames, we will have 16 minus 1, or 15 difference frames. As explained earlier, if two frames are identical, they will difference to all zeros. Depending on the method used for displaying this frame of all zeros, it will be scaled to display as some solid shade of gray, usually black. If the two frames are not identical, then there will be a variance in the difference frame. This variance is known as clutter leakage. As we will see later, clutter leakage is a particular problem in the vicinity of distinct high-frequency edges within the frame. Examples of high-frequency edges are roads, shorelines, buildings, etc., which exhibit high contrast with the neighboring pixels. Let's look at the ideal case where a sequence of backgrounds are identical and a target is flying through. We will look one at a time at a sequence of 4 frames. Frame 1 is shown on the left, frame 2 is in the middle, and their difference frame is on the right. Frames 1 and 2 are identical, except for one black pixel in each frame. Notice that the black pixel has moved 1 pixel up and to the left, from frame 1 to frame 2. The black pixel represents a simulated target flying through the field of view. The difference frame, which has been rescaled according to the new minimum and maximum pixel values, clearly shows the location of the target. The black pixel, the lowest negative difference, shows the position of the target in frame 1, while the white pixel, the highest positive difference, shows the position of the target in frame 2. The rest of the pixels in the difference frame are 0 and are scaled to display as gray. Now let's advance to frame 3 of the sequence. Again, frame 1 is shown on the left, but this time frame 3 is shown in the middle. Notice that the target has moved another pixel up and to the left. As can be seen, this movement is also reflected in the difference frame, which is on the right. The black pixel still shows the position of the target in frame 1, while the white pixel now shows the position in frame 3. And again, we see the pattern progress another step in frame 4. This example is trivial, since the background didn't change. When the background changes, this task becomes more difficult. Let's look again at the 3-loop movie sequence of Lake Mead and see the effects of differencing as the background changes. The loop movie on the left has 0 background change. The loop movie in the middle exhibits a small background change, jitter, and the loop movie on the right demonstrates a lot of background change. Let's look at the sequence of difference frames created from the no jitter case on the left. As predicted, the background differences to a solid shade of gray, and the target stands out clearly. Again, this case is trivial since there was no background change. Notice, by the way, how the shape of the target changes as it moves. This is caused because the target, at times, overlaps into other pixels. As a result, its energy gets split up. The difference sequence of the small jitter frames shows the clutter leakage phenomenon. Notice in particular that the high frequency or high contrast areas of the original scenes, such as the shorelines and the small canyons, leak through the most strongly. Even with jitter up to 0.5 pixels, the detectability of the target was still increased by the differencing. Finally displayed is the result of differencing the big jitter sequence. This time we see that as the background jitter increased, so did the clutter leakage in the difference frames. Note, too, that we still can't see the target in this sequence. The fact that we can clearly see or detect the target in the first two sequences is one thing, but can a computer detect it? Whether or not a computer by itself can detect the target will be the true test of our enhancement process. The test will be simple and straightforward. If an unbiased computer program can recognize the fact that there is a target moving in the frames, and if it can distinguish this target from the background clutter noise, then we will consider the target enhancement algorithm a success for that data set. Otherwise, it fails. An algorithm known as the TRACS algorithm is capable of performing these tasks if the data is sufficiently enhanced. We will use it here to judge the enhancement method. In other words, the target will not be considered detectable unless the TRACS algorithm can see it, regardless of how well we can see it. By analyzing the temporal and spatial intensity changes, the TRACS algorithm works by searching for pixels in each frame that exceed a specified minimum intensity. Progressing from frame to frame, the TRACS algorithm then looks for continuous linear patterns of these pixels. If a pattern continues to grow throughout the frame sequence, and if it eventually reaches a predetermined length, the TRACS algorithm displays it as a white streak across the computer screen. Shown here is a demonstration of how the TRACS algorithm works. On top is a two-frame sequence of enhanced frames showing a target moving from one position to the next. On the bottom, the TRACS algorithm creates a black and white image which plots this path. As the target progresses in subsequent frames, the TRACS algorithm continues to build the track. Because the final TRACS image consists of only two different intensities, black and white, a computer can now easily identify the target track. In cases where enhancement was insufficient, and as a result, clutter leakage is extreme, the TRACS algorithm may be misled to follow false tracks. When the TRACS algorithm first begins analyzing a sequence, it will usually attempt to follow several false tracks. But these should be eliminated as more information becomes available in subsequent frames. Ideally, only the true target will have had the consistent strength to remain once the entire sequence has been analyzed. If false tracks remain at the end of the sequence, then the target is considered undetected. Let's apply the TRACS algorithm to the Lake Mead data that we have already differenced and see how it performs with the different levels of clutter leakage. In the no jitter sequence with no clutter leakage, the TRACS algorithm performs perfectly and easily calculates the target's path. Even with a small amount of clutter leakage, the TRACS algorithm still manages to build a track that is very close to accurate. Notice in the first several frames of the sequence that many false tracks appear. Since these false tracks don't continue consistently in a straight pattern, though, they are eliminated as more frames become available. At the end of the sequence, only the actual target track remains. We have a successful detection. As predicted, the TRACS algorithm was unable to detect any sign of the target in the big jitter sequence after it was differenced. In fact, it calculated that some false tracks looked more like the target than the real thing, and wrongly determined them to be targets. Although we can't see the target in the original big jitter sequence, it is there. As was shown in the no jitter and small jitter sequences in a relatively stable background, the target was strong enough for detection. But when the jitter got too large, the target's signal was overwhelmed by the clutter noise, and simple frame-to-frame differencing was unable to bring it out. What if we had a way to remove the jitter and make the background stable before we difference the frames? This should reduce the clutter leakage in the differences and thus increase the target's signal-to-noise ratio. Would we be able to detect it then? This thesis will show that background stabilization will make this target detectable. We can't make it as strong as the no jitter case, but it can be made more detectable than it was under the small jitter conditions. The background stabilization target detection algorithm performs 4 basic functions in order to enhance the target. 1, it measures the frame-to-frame jitter. 2, it removes or corrects for the jitter. 3, it matches the blur between frames. And 4, it applies the simple differencing algorithm which we have already seen. Measuring or estimating the jitter is the most complicated and critical step in this algorithm. An incorrect estimation could worsen our chances of detecting the target rather than improve them. Therefore, it's important that the estimation be as accurate as possible. Estimating the jitter means to try to calculate as closely as possible how much one frame is shifted from another. If the shift is greater than 1 pixel, as we have here, we say that it is multi-pixel shift. If it is less than 1 pixel, we say that it is sub-pixel shift. Background stabilization uses a 3-step process to estimate the jitter. First, it estimates the multi-pixel shift to the nearest pixel using a method called shift and correlate. Second, it takes the result of the multi-pixel shift calculation and uses a combination of bilinear interpolation and, again, shift and correlate to refine the estimate to the nearest quarter pixel. Lastly, it uses a method developed for this thesis called slope climbing to fine-tune the estimate to be very close to the true shift. Tests on simulated data indicate that this last step is very accurate, with an average error of approximately 0.07 pixels. It requires, though, that the shift be less than a quarter pixel. Step 2 assures this for us. Estimating the multi-pixel shift to the nearest integer is the simplest part. These 2 images clearly show a large shift from one to the other. Let's see how we can measure how much frame 2 is shifted from frame 1. First, we choose a subset, which we will call a window from the center of frame 2. Then, in a systematic fashion, we will move or slide another window to all possible positions on frame 1. Each time we slide the window to a new position, we compare the regions within the window areas to determine how well they match. Our goal is to find the best match. This will tell us our estimated multi-pixel shift to the nearest whole pixel. The correlation function, which we will identify with a lowercase r, is used to determine the best match after each shift of the window. As a result, this method for estimating multi-pixel jitter is known as shift and correlate. We base the accuracy of our estimation on the observed correlation value of the pixels within the window, where a correlation of 1.0 indicates a perfect match and 0 indicates no match at all. Ideally, we want to achieve a correlation above 0.9. Before we begin our jitter estimation process, let's compare the 2 frames just as they are. We'll do this in 2 ways. First, let's difference the 2 frames and note the clutter leakage. Recall that the more 2 frames are similar, the less clutter leakage we should expect in their difference. In order to quantitatively evaluate the clutter leakage, we will relate it to the standard deviation of the image intensity in the difference frame. A high standard deviation implies a large clutter leakage, while a small standard deviation implies a small clutter leakage. The standard deviation here, sigma, is almost 3,000, which is very high considering that the total range of the data is only about 12,000. This, along with the clutter leakage, tells us that these two frames are not very similar at all. Second, let's calculate a starting correlation value for the two frames by comparing their center regions. We come up with a correlation value, R equals 0.524, which, as one would expect from looking at the two frames, is far from a perfect match of 1.0. We'll use this value to mark our improvement later. Now let's start our multi-pixel shift estimation. We start by moving our window on the left frame to the lower right corner, and then shifting it pixel by pixel, line by line, until we reach the upper left. Each time we slide the window, we recalculate the correlation value by comparing the two windows. We keep track of the highest value obtained and the shift position that yielded that value. When we get done, the shift of the position that had the highest correlation, R, tells us the approximate shift between the two frames to the nearest pixel. We can see that the highest correlation was R equals 0.899 at an integer shift of 3 pixels down and 3 pixels to the right. Notice the similarity in the two windows when we shift it to this position. Once we have the integer shift estimated, we can correct it by merely getting rid of the excess 3 rows and columns in frame 2. And then moving the origin 3 lines up and 3 pixels to the left. If we throw away the opposite rows and columns from frame 1, we then have 2 nearly identical images. Of course, our images are now smaller because we threw away the parts that weren't common to both images. Let's difference these frames to see how we're doing. We now have a standard deviation of sigma equals 535 in our multi-pixel corrected difference frame. Comparing the clutter leakage now to the clutter leakage of the difference of the original frame, we can see a big reduction. This tells us that the two images are more similar than they were before. We still have to do better, though, if we want to detect small, weak targets. We also need to calculate the fractional part of the shift, the subpixel shift. Estimating subpixel shift is considerably more complicated. A paper entitled Subpixel Image Registration by Kwai-Tan provides a complete analysis of various methods which have been proposed or which are in use to measure these small shifts. The second step of the estimation process, used for background stabilization, is a method Tan calls intensity interpolation. He claims an accuracy of down to 0.05 pixels, but admits that it is very time-consuming in order to achieve this accuracy. At this point, we are only after a 0.25 accuracy, which can be done very quickly, approximately 20 times faster based on the number of calculations that need to be performed. We will then improve our 0.25 estimation to almost equal Tan's 0.05 later with the slope climbing method in step 3. The intensity interpolation method is a variation of the shift and correlate method used to estimate the integer shift. The difference is that at each pixel step, we do several comparisons instead of just one. In between each comparison, though, we modify the window to approximate what the image might look like if it were shifted to each of the quarter pixel increments 0.25, 0.5, and 0.75 from the current position, both horizontally and vertically. Since we already know the shift to the nearest pixel, we only need to check for fractional shifts up to half a pixel in each direction from what we already have. Bilinear interpolation will be used to modify the window. It allows us to modify the intensity values of the pixels to give the appearance of shifting. Bilinear just says that we are trying to calculate the shift in two directions, horizontal and vertical. Interpolation means that we will approximate the value of a pixel after a quarter pixel shift by calculating a proportional value in between the two nearest integer pixels. Here again, we have one of our simulated images of Lake Mead. Let's zoom in again to a 4x4 and see how interpolation can be used to approximate a quarter pixel shift of the image. We're going to make our task easier here by approximating the shift in only one dimension, horizontal. Approximating the shift in both the horizontal and vertical dimensions, as we have to do to accurately estimate both the horizontal and vertical shift, is a bit more complicated, but uses the same principle. First, let's view this image as numbers rather than shades of gray. We'll perform the calculations on the pixel in the second row, third column. It currently has a value of 16,054. Remember that the intensities of this image are scaled such that pixels with values in the 9,000s display as black, while pixels in the 20,000s display as white. Values in between are linearly scaled to the various shades of gray. If a real image is shifted to the left, that means that the sensor moved to the right. In this case, the sensor, which is currently seeing the shoreline in our selected pixel, would see more water and less land after a quarter pixel shift. We would expect then that the pixel would become darker and that its numeric value, now 16,054, would become something less. The pixel to the right of this pixel, which has a value of 9,838, will also play a part in the interpolation. To calculate the new value of our sample pixel, in order to approximate a quarter pixel shift, we interpolate by simply taking 1/4 of the pixel on the right, add it to 3/4 of the selected pixel, and the result is the new interpolated value. In this case, the new pixel value would be 14,500.25, which we round off to 14,500. As predicted, the new value of 14,500 is somewhat lower than the old value of 16,054, thus approximating the pixel averaging more water than before. As a result, the pixel is now darker. If we perform this same calculation to every pixel in the image, we will cause the whole image to appear as if it moved a quarter of a pixel to the left. Let's watch this happen. Here we see the image before the approximated shift, and this is the image after the shift. If we want, we can continue to recalculate the interpolations over and over to approximate drift. We can see how accurate these approximations are by comparing the approximated shifts to actual simulated shifts. The simulated shifts will be shown on the bottom. The approximations appear to be pretty good. You have to look closely to see a difference. The shoreline pixels probably show the difference the best. If we go back to the full frames, we again see that the approximation of shift is pretty accurate. The approximated shifts are on top, the simulations are on the bottom. If we look closely, we can see a problem caused by interpolation. Notice how the interpolated frames seem to blur while the images are shifting. This is an artifact of the interpolation method, and it will cause us trouble later. The blur is the worst when the frame is interpolated half a pixel. There is no blur when the interpolation is integral. Here again are the two frames which we corrected earlier for multi-pixel shift. Getting back to our problem of estimating the sub-pixel shift to the nearest quarter pixel, we now simply take frame 2, which has already been estimated and corrected to the nearest pixel, and interpolate it at quarter pixel increments in order to refine our estimate. To do this, we again create a window in each frame in approximately the same location in the center. Using interpolation this time, we approximate all of the different quarter pixel shift positions up to 3/4 of a pixel from the center of frame 2 and correlate it to the window in frame 1. As was previously pointed out, since we already assume as a result of the multi-pixel correction that we are within 1 pixel of the true shift, it is not necessary to interpolate more than half a pixel in either direction. We go 3/4 just to be safe. Each time we see the window in frame 2 change, it is being interpolated to another 1/4 pixel increment. The interpolation increment that yields the highest correlation gives us our new refined shift estimate. In step 1, we estimated that the frame on the right was originally shifted 3 pixels down and 3 pixels to the right from the image on the left. With step 2, we can now improve our estimates to -3.25 and -3.00 respectively. Now that we have our 1/4 pixel estimate, we can take frame 2, already corrected to the nearest pixel, and approximate the new estimated shift correction by interpolating it 1/4 of a pixel up. You have to look closely to see it change. These two frames are now even more similar. Note that our correlation has now increased to 0.988 from 0.524. Remember, 1.0 is perfect. If we difference the two frames, we can see that the clutter leakage and standard deviation have been reduced even more compared to the differences obtained earlier in our estimation process. Another indication that our estimation and correction are getting pretty close. We can still get closer, though. The third part of our jitter estimation process is not as obvious as the first two parts, but is very accurate for estimating shifts that are less than 1/4 of a pixel. First, let's define the algorithm and then explain how it works. The slope climbing algorithm relates the spatial intensity slopes across each pixel in frame 1 to the change of intensity of each pixel from frame 1 to frame 2 into a set of simultaneous linear equations. The solutions of these equations will yield a pair of best fit shift values which closely estimate the shift between the two frames. Let's first see what we mean by the spatial intensity slopes in frame 1. Each pixel in an image has an intensity, and this intensity changes from pixel to pixel. From any location within the image, if we travel along a straight path from one point to another, the intensity either increases, decreases, or stays the same as we move into each new pixel along the way. The rate at which this intensity changes is what we call the spatial intensity slope along that path. The line being drawn at the bottom shows the relative horizontal intensity slope of each pixel being crossed over by the line being drawn on the image. If the intensity changes very quickly, moving between two very close points, such as neighboring pixels at the shoreline, we say that the intensity slope at that point is very steep. On the other hand, if the intensity changes very little throughout a large portion of the image, then the slope is fairly flat. For any given pixel, we can approximate an intensity slope across it, along both horizontal and vertical paths, by analyzing the intensities of the pixels around it. For instance, if we want to examine the horizontal path slope across a pixel at the shoreline in this image, we only need look at the neighboring pixel on shore and then at the neighboring pixel in the water to see that the horizontal path intensity decreases as we move from left to right. As a result, the horizontal path intensity slope across the pixel on the shoreline is negative, since we are going down in intensity as we move horizontally across that pixel. The vertical path intensity slope for the same pixel can be determined in the same way, by analyzing the neighboring pixels above and below it. An approximation for the slope across a pixel can be calculated by dividing the intensity difference between the neighboring pixels by 2. For example, to approximate the horizontal slope, we can simply subtract the intensity covered by the pixel on the left, which we will call I1, from the intensity of the pixel on the right, I2, and divide the result by 2. This gives us an approximation for the slope. We perform the same procedures to approximate the vertical slope, except that we subtract the top pixel from the bottom pixel. Now that we have the intensity slopes for that pixel, we next look at how much that intensity has changed in the same pixel in the next frame. We can now relate the intensity change to the slope as a simple linear function of the shift. All that is left is to solve the equation for the shift, and we have a very crude estimate based on 1 pixel. To improve our estimate, we derive the linear equation for each pixel in the frame, and then, using the method of least squares, solve for 1 pair of shifts which most closely satisfies all of the equations. This is our final answer for the estimated shift between the 2 frames. Here again we have our 2 frames which we have previously registered to within 1/4 of a pixel. If we apply the slope climbing algorithm to these 2 frames, it tells us that they are shifted from one another by approximately minus 0.053 pixels vertically and plus 0.129 pixels horizontally. This, combined with the results of the intensity interpolation and multi-pixel estimations, adds up to a total of minus 3.303 vertically and minus 2.871 horizontally from the original frames. By again using bilinear interpolation, we can correct for the last small bit of jitter that we could estimate and make these 2 images practically identical. This final correction is so small that it will be difficult to see. Watch as we make the correction in frame 2. As was already mentioned, the slope climbing algorithm has proven to be very accurate at estimating the shift. Based on extensive tests performed on simulated data where known shifts ranged up to 0.25 pixels, this algorithm usually produced estimates within 0.1 pixels of the true shift. The true simulated shift between our original 2 test images was minus 3.375 vertically and minus 2.875 horizontally. Our estimation was off by only 0.06 of a pixel. The correlation value for these 2 images is now 0.994, almost a perfect match. Recall that we started with 0.524 and improved it after each step. The difference frames also show a marked improvement after each step. Shown here is the difference of the 2 frames after the final correction. The clutter leakage and standard deviation are now very small compared to what we started with. Another way we can see the improvement in our jitter removal is to view the frames before differencing and switch rapidly between frame 1 and frame 2. As the jitter removal gets more accurate, we should see less change frame to frame. Here we see 4 copies of frame 1. And here is frame 2 for each step along the way. We will now switch back and forth rapidly between the 2 sets of frames, and the improvement should be very noticeable. But there is still one last thing that background stabilization does to reduce the clutter leakage in the frame difference even further. Remember the blur we pointed out earlier as we were interpolating frames? You can probably notice, too, that the corrected frame 2 on the right appears more blurred than the frame 1 on the left. This blur is an undesirable byproduct of interpolation. The difference in blur between the 2 frames adds to the clutter leakage. Ideally, it would be nice if we could now remove the blur from frame 2 to make the 2 frames more similar, but this isn't possible because too much information was lost during the interpolation. We can, though, degrade frame 1 to make it appear more blurred, thus making the 2 frames more alike. We can do this by applying an equal amount of interpolation to frame 1 as we did to frame 2, so that the frame does not appear to shift, though, as we interpolate it in opposite directions at the same time. This gives us the effect of blur without the effect of shift. Watch frame 1 closely as we use this method to blur it, similar to frame 2. There is now little difference between the two frames. It might be argued that blurring frame 1 will also weaken the target that we are trying to detect. This is true, but since we will be differencing all of the frames in the sequence with frame 1, we really don't care if the target is in frame 1 or not. In frame 1, we care only about the background. By blurring frame 1, we actually make the target seem stronger in the other frames because the background cancels out better in the difference. After blurring, our frame correlation has now improved from 0.994 to 0.998. As expected, our difference has also improved. On the left is the difference after jitter correction, and on the right is the difference after adding the blur. Our standard deviation has now decreased to 182, and the clutter leakage is almost non-existent. We've come a long way since our original frames. Let's rapidly switch the frames again, this time including the frames after blurring. Notice how each time we improve the jitter estimation and removal, that the change between frames 1 and 2 becomes less, and after blurring frame 1, we hardly see a change at all. We have taken two very shifted frames and made their backgrounds almost identical. As a result, the clutter leakage in their differences is very small. Now that the backgrounds cancel out so well in the differences, anything else in the scene, such as a target, should appear very strong. This completes the background stabilization process. Let's now apply these steps to some unstable data sequences that contain targets that have previously been undetectable, and see how well background stabilization performs. Let's look first at the sequence we saw earlier where we already failed. Displayed here are the three loop movie sequences on which we previously demonstrated the target detection process. Recall that we were unable to detect the target in the big jitter sequence on the right. Let's try it again, this time applying background stabilization before we difference the frames. If we apply background stabilization to all 16 frames in this sequence, such that each frame is jitter corrected to match frame 1, the sequence will then appear like this. Notice that the stabilized frames are now much smaller than the frames in the original jittered sequence. As pointed out earlier, this is because only the region of each image, which is common to all of the images, is used to make up the stabilized sequence. The rest is thrown away. Normally, the original frames are much larger than those in our test sequence here, so this will not usually cause a problem. If you look carefully, you can see the target. Just by correcting for the jitter, the target has now been sufficiently enhanced to make it visible. Differencing each of these stabilized frames with an equivalently blurred frame 1 enhances the target even more. Recall that when we differenced the original frames, the clutter leakage was so bad that the target was completely lost. Now, because the background jitter has been corrected such that the backgrounds are all similar, the clutter leakage is very small and thus does not obscure the target. If we apply the tracks algorithm to the stabilized difference frames, we now get a well-defined target streak, unlike the false tracks we obtained earlier. Based on our testing criteria, we have successfully detected the target using background stabilization where we could not before. Before we finish, let's quickly look at 5 typical types of data sequences where targets were undetectable using conventional detection methods but were successfully detected after background stabilization. We will first look at another sequence of big jitter. Although we have already demonstrated success with big jitter, this sequence is a bit more realistic since we have larger frames and more clutter. This will make it a more difficult test than our other demonstration sequence because there is now a greater likelihood that false tracks can appear along the shorelines and canyons. First, we correct for the jitter. Then we blur and difference. And finally, the TRACS algorithm reports another successful detection. Our second typical sequence is an example of big drift, where the target is moving in the same direction as the drift. Recall that the direction of the drift is relative to the motion of the sensor, not to the direction the images are moving on the display. The sensor in this case is moving up and to the right. This is the same direction that the target is moving. This type of target motion is called in-track, and as can be seen, the target is successfully detected. Case 3 is another example of big drift, but with the target moving in the opposite direction. This type of target movement is called minus track. The target is moving in the opposite direction from which the sensor is drifting. The next sequence, again big drift, is an example of where the target is moving perpendicular to the direction of the drift. This type of target motion is called cross-track. This last sequence is a special case known as auto-track. Normally, it is of only experimental value because we already know where the target is. Auto-track data is similar to the big drift in-track sequences, except that the sensor is locked onto the target. As a result, the target appears to be motionless in the frames, while the background moves by. Even strong targets are difficult to detect in sequences such as this, since the target cancels out with itself in the difference. In other words, if the target is in the same position in 2 frames, it subtracts to 0. That's what we want the background to do, not the target. By stabilizing the background, we, in effect, cause the background to stand still and make the target move. Now, with the combination of a stationary background and a moving target, we can successfully difference the frames and detect the target. Problems encountered in trying to detect targets in auto-track data is what originally prompted the idea of background stabilization. This presentation has shown that target detection is still possible in data sequences with large frame-to-frame shifts. As has been demonstrated, if the unstable frames are resampled in order to make their backgrounds appear stable, then it is possible that the targets can still be enhanced.